very brief background from you. I mean, I maybe this is wrong, but you did a PhD in Erlangen, right?
No, no.
Okay.
Sorry. I did a PhD in computer science in Nanjing University in China.
Okay.
Then I did one postdoc in USDC in China for experimental quantum optics. And then later I did another postdoc in Erlangen. The research idea is more like AI for science in Erlangen. Yeah.
This postdoc you did it with Jan Ole, right? And Carla, who are from Spain in Mario Cren's group.
Yeah.
Okay, I think so. There were more people from Barcelona in that group, maybe, and also Carlos.
Yeah. Carla and Carlos are from Spain. Yes. Now
So
they are.
Carlos,
Yeah.
yes.
Sorry.
He was like they are from the same university than we are.
Oh, nice. Yeah.
Yes.
Cool.
And currently you are starting your own group.
Yes, I start my own group this year, February. Also not so new, but also recent, like start not so long time. Yeah.
Congratulations.
So thanks a lot. So now I'm in Jena, University of Jena, in another city, not in Erlangen, but not far away. Also, my previous group, like Mario Kern's group, he is also moving. He has already moved to Tübingen. Yeah.
There is a Max Planck Center in Tübingen, or?
No, he went to Tübingen as a professor in this university. Although there are some other Max Planck Institute in Tübingen that's mainly for intelligent system, pure computer science, and so on.
I see. Okay. Well, wow, impressive. Okay, so thanks again a lot. And if you want to start the seminar, the floor is totally yours.
Oh, okay, cool. Thanks. So thanks a lot for the invitation. So today I'm going to talk about our work about use AI to design or discover new experiment or research ideas in quantum physics and in physics in general. So I will start with with this outline. First, I will talk about how we use AI to discover new experiment, particularly in quantum optics system. And then I will explain how we can use AI to find new research directions or research collaborations for scientists. And then the more ambitious goal is more like go towards artificial scientists from idea generation to experimental implementation. So first, I will talk about how we can use AI or machine learning to design new experiment in quantum optics. So imagine, usually when we do experiment, we usually collaborate with theorists, or we come up have some conversation about how to design certain experiment for some purpose. For example, generate certain quantum state or some quantum transformation. So what we usually do is we go to the write in a paper or discuss with theorists or write in a black box, discuss and in this in several rounds. And then sometimes we can find some solutions. Sometimes we take a very long time to find solutions, or maybe even take very, very long time to find a solution, or maybe not even find the solutions. So you can see the thing that the underlying thing is that the search space, the design space of experimental setup is enormously large. For example, if you only have like a 3-beam splitter or 3-beam splitter and some phase shifters, the combinatorial space already goes very large. So it's very time consuming if you want to find some useful experiment. So, but we can think in a different way. So we can start thinking in that way that we can consider all the experimental space, experimental setups are in a abstract space. So you can consider that you have an abstract space of all possible experimental setups. Every thought in this space are some experiment. And for example, there are some experiment with exceptional and useful properties. Like, for example, like this stuff. There are many probably. And the human scientists or researchers have used their intuition or knowledge already find some solutions. And with this combinatorial space, it's enormously large. So AI can help to find some solutions as well. And for example, for this case, particular case, this means that the AI or computer will discover the same technology as the human scientists find, or even like the machine, the computer finds some ideas that inspired by human researchers' ideas. Or even better, it's like it can find some ideas that or technologies that entirely new. And this space is enormously large. So with a machine, so it's possible to find more ideas. So that's why computers or AI is very helpful in this combinatorial search space. But how can we discover new quantum experiment? How can we use computer to design a new experiment? The workflow is quite simple. So it's like you start with a large search space, which contains basically all possible experimental configurations, like as many as possible. We try to make it very large such that you can do a discovery instead of simple optimization. And then from this large search space, you have some physical simulator or quantum physical simulator that can simulate the setup. You have some certain setup, and then it gives you the output. And then you define some scientific objective, namely the interest or the quantity that you are interested or you want to achieve, or that you want the purpose of the setup to do. And with the objective, then you can later apply some AI-based exploration. For example, the simple case is like, for example, gradient descent optimization or some other optimization techniques, and then try to change the parameters or go to a different setup in this large search space. And you repeat this processing until it converges and find many setups. So this is the rough workflow for how you can use a computer to design or discover new quantum experiment. And let's start with a simple case. It's like, for example, this is a three-dimensional geometry state. You can consider that it's like 3 photos encoded in color. It could be blue, red, and green, or you can encode in different ways, like orbital angular momentum or time being and so on. So the thing is like, how can we implement experimental setup that produce such a quantum state? So one can, as I said, we can try to play around with the optical element and then see how we can get to the setup. But the combinatorial space is very large, and it's not so easy or not so fast to find a solution. So it would be nice that you can have a, like I give you some optical element and some objective, like the purpose, the quantum state that I want to produce, and then you have the computer to do something inside, and then it give you the solution, and later we can implement in the lab. So the workflow is like the first idea use a computer to design experiment is from Mario Ken in 2016. The idea is like they have this toolbox, which is like a lot of optical elements, and they random generate a setup. And from there, they calculate the quantum state respect to the setup, and then check whether it is interesting or it fulfills their condition. If it fulfills the condition, they further simplify the setup and then report the result. Of course, they also add the simplified setup back to the toolbox such that it can try to learn learn to use the solutions and then make it as a like building blocks for further applications. And with this simple idea, it can already find several setups. For example, can like find the first experimental setups for producing high-dimensional gesture state or high-dimensional multi-particle entanglement state, or even new ways to control measure photons in different degree of freedom and a special type of transformations, and also find new ways to construct a multi-particle entanglement with a path identity. So the old method is very powerful. The problem in the old one is that it starts with a random setup. So it generates a random setup for certain optical elements. For example, they write in this symbolic way, and then calculate the property of this setup. If it doesn't work, then they generate a new setup again. So this is more like infinite and discrete exploration space. So it's not, one cannot use gradient descent in this particular case in their old algorithm. So can we do something slightly different? So we can think about in a different way. So we can represent an experiment as a graph. And then we can, like each experiment is a graph, and then we can make it as a finite and then use a continuous space to do the optimization. So each optical element, each optical experiment is like a weighted graph, and then one can just apply some continuous optimization techniques to change the weights and change the weights of the graph and then get the setup. So the representation is quite I will explain in a simple way. So let's say we have a setup like this, and then it can be represented as a graph. This is just for example. This is a simple example. It can be a very complicated one, and then the graph will be slightly different. So in this case, the graph is an experiment, and the experiment is a graph. And the vertex in the graph means the photon to the detectors, and then the edge is means the correlated photon pairs. In a simple case, you can consider as a nonlinear crystal like a BBO or PBKTB nonlinear crystal that is widely used in the lab for producing photon pairs or producing an entanglement state. And then the edge width is the amplitude of the photon, and the color of the edge means the like the photonic mode, like degree of freedom of photon in the path. So this is a simple representation. And with this representation, we can frame the question in quantum experiment as a graph theory problem, or we can also look at graph theory problem and translate into a experimental setup and try to see whether one can simulate a graph theory problem in experiment. And with this link, one can already find some new interference effect, and this has been implemented by several experimental groups. But the most powerful thing is that, as I said before, it's like we can use this abstract representation to do design. So each experiment is a graph. So now we start with a large search space. Namely, in this case, we start with a fully connected graph. Here has some edges are disconnected because we have some constraints in certain resources, like we don't allow the photon in path 0 and 3 are intact before. So that's why there's no edge between them. But the idea is like you start with a fully connected graph that represents the large search space because it contains basically all the possible combinations in the setup. And then you define some loss function as I said before, it's like the scientific objective that you want the experiment to do. And then we apply some continuous optimization techniques such as gradient descent you can also use other optimization techniques. And in addition, we add some topological optimization. Then they try to reduce the number of edges in the graph such that we want to have a simple graph. Because with a simple graph, we can easily try to understand it and also translate it into an experiment that is simple to implement. So this is a workflow to how we can use a computer to design experiment in this particular representation. And with this workflow, we can already task with different target to find different type of entanglement state or some other quantum of transformation, like some certain gates and so on. For example, we task with 100 different questions. And particularly interesting is that one of the solution has already been implemented by an experimental group in Nanjing. They find our PySUS give a new solution that you can entangle independent photons that have not interacted before in a different way. So the traditional way you entangle independent particles that have never interacted before is using entanglement swapping, but our computer give a different way that you don't need to use. It's a different type of entanglement swapping. You don't need to produce entanglement in the beginning, and you also don't use a Bell state measurement. It only uses the Pi's identity, and then the coherent superposition of the crystals. So this has been done in the experiment, so which is very nice. And we also share the code in the GitHub. So if you're interested, you can have a look. And this workflow has already been also been applied in other fields, not just in quantum optic experiment, but it can also be used in classical optic systems. For example, this has been done in finding new microscope. So there, the large search space is the gray, like the gray dark background. This somehow they construct such a large space, and then this is just one solution found in the large space. And similar idea can also be applied in these gravitational wave detectors. Find new ways to design new gravitational wave detectors or interferometer scheme. So these are the things that one can use this computer to design new experiment. But the thing is, like, what if the physical simulator is too slow? Then one can do a slightly different thing, that we can replace this physical simulator as by a neural network simulator. Then this will be faster. Additionally, one can also write this physical simulator in a very high performance way, such as write in JAX, as this X-numerator for the classical microscope used. So the thing we do now for this, if you want to replace with a neural network, one thing we do is like we take the idea from deep dreaming, which is usually in this computer vision field. So it's like you train a neural network and then with many images, and let the neural network or let the model to generate new images. So the idea can be explored in experiment design. So namely that we because we have this physical simulator, we can use the physical simulator produce many setups represent in graph, and then we hot encode this graph and to this to some neural network and train it respect to the fidelity of the quantum state generated by the graph or generated by the setup, and then we train it. Once it's trained, we then fix the neural network. We don't change the weights and bias inside the neural network, but we ask the neural network to change the input by optimize the towards to the target that you want. So with this, then we can do also somehow ask the computer to design experiment for certain quantum state. Namely, we replace the physical simulator with a neural network. And then we can see that we can give some random graph that is with fidelity for certain states, like GHZ state lower than 0.5 fidelity, but the model can try to come up the setup with perfect fidelity or higher fidelity. additional thing that one can look into, because it uses the neural net, so we can look into further. We can look into the neural network, see what the neuron is active, and then see how the information goes through the neural network. So it more goes towards to the interval AI. Similar ideas can be applied here, that you can use a variation autoencoder, encode each setup, and then you decode it. And in this lower dimension space, and you can look at the properties of maybe certain optic elements, which is very important in certain experiment, and try to look at which optic elements play an important role in the final scheme. So these are different ways to do experimental design. With that, but then one thing is that, there are a lot of papers or scientific knowledge online everywhere, or in the journals and so on. So we, in the previous talk about design new experiment, we define the large space and we define some scientific objective. But what if the experiment has already been done, or the idea is somewhere in some literature or some papers that we maybe don't aware of? So how can we take advantage of this? So the idea is you can see that the number of submission to arXiv is growing very fast, particularly in certain field like machine learning or AI. The number of paper grows even exponentially. So how can we take advantage of all this scientific knowledge that already developed by scientists to develop a tool that can inspire interesting or impactful ideas for researchers? So the problem is, how can we do that? There are so far I think there are two ways. One is use large language, because before the large language is not so powerful. Nowadays it's very powerful, so one can think about use language models to interact with the literatures, or even fine-tune a language model with the scientific papers to do idea generation. But this is not very feasible for individual researchers. So the one idea here is we can build a knowledge graph from the scientific literature. So what does that mean? Is we can take the papers, for example, namely the title and the abstract, and then we extract some information from the papers. Even we can extract a little bit information from each paper, but because the number of papers is very large, so when you extract many times, then you can already have certain patterns from the knowledges from the scientific literature. So the knowledge graph is represented in like this way. So the node in the graph means the topic, or you can call it concept or research topic. And then the age is drawn only when the two concepts appear in one paper. So namely, if they appear in one paper, then there's an age between them. And then because it's a publication, so usually it has the time information. So the age also carries the time information. So with that, you can try to build a large knowledge graph, like a very large knowledge graph. And with this, it already somehow captures the a research knowledge from the past in a dynamic way from this knowledge graph. And because it's time dependent, and with machine learning, we can think about how can we use the knowledge graph to predict what will happen in the future. So this can be phrased as what unconnected pairs of concept will be investigated later in maybe 5 years or 3 years and so on. Because unconnected pairs of concept means the two topics haven't been investigated. So with that, then you can apply some machine learning method. Now, it can be phrased as a link prediction problem. So you can use past knowledge, and then you give to a neural network and predict what will happen, whether they are connected in the future and so on. In this case, we don't directly input the large knowledge graph to a neural network, but we handcraft some features and then give to a neural network for each unconnected pairs. You create some features. One can do something differently. With that, then you can later train a new model and then apply with like the unconnected pairs from counter year and predict what will research do in the future. Now, one more important thing is that, okay, you predict what the research will do. Sounds interesting, but if you can predict what the research will do will be impactful, that will be more interesting for scientists. So then the question could be that which scientific concept that haven't been investigated jointly, namely unconnected pairs, in the knowledge graph, that will have certain citation bigger than certain number in 3 years and so on, because there's no good quantitative impact. So we use citation count as the approximation. And then similarly, we will build a knowledge graph. We take the papers from archive, bioarchive, and meta-archive, and chem-archive, and so on. There we use the abstract and paper, abstract and title, and then extract the concept. And then, of course, we look into certain domains. So we select the concepts in the domain-specific field, like optics and quantum physics. And then this corresponding to the node in the knowledge graph. And then because we want to have some citation information, so we use another dataset from OpenAlex and then construct the edges between the node. So therefore, you can create a large knowledge graph that is also time dependent, but each edge also carries the citation information for each year and total citation information and so on. So it's citation-enhanced knowledge graph compared to previous one. And then you can, and then now we do the same thing similar. We take the unconnected pairs from the past knowledge graph, and then we extract some features, extract roughly 144 features, and then give to a neural network, and ask the neural network to train it to train with, like in the future, it has certain number of citations. And we did this with different threshold, like whether it will have citation bigger than 100 or smaller than 100 or bigger than 50 and smaller than 50 and so on. And then we use ALC undercode to quantify the classification problem. Because in the end, this question is a binary classification task, and then the quantity is quite good. And then we can try to train another neural network and then evaluate, and then we apply to the future data to predict what will happen in the future. With this, then one can think about use this model to suggest impactful or research directions. So one can do personalized research topic suggestions, namely that we take the concept from your field, like from your papers, and then respect to the knowledge graph. So you can extract the unconnected pairs between you and then the knowledge graph, and then apply to the trained neural network, and it will give you a ranked list of ideas. And also we can do research collaborations, namely that you have one concept from research A, another concept is from research B, and then you extract the unconnected pairs between them and then apply to the trained neural network. And it will give you the ranked suggestion pairs, which research topics that you too should work on. But what about this only gives you the concept pairs suggestions. So further, we go a bit further that what about we can give a bit more concrete ideas or research questions towards to these research directions. So we can now we plug in some language model, namely that we take the papers from the two researchers and then extract the concept from them. So then this means we have two sub knowledge graph in the large knowledge graph, and then we can extract the unconnected pairs or even random combination of the concept pairs, and then give to a language model, namely ChatGPT, and then we also give the research information like from their recent published paper, or some additional information from the two researchers to the language model, and ask the language model to formulate a research project or research direction that the two research might find interesting, and give the title and the objective and also the research questions in this project that could be interesting for the researchers. And we also ask ask 110 group leaders from the Mask Brown Society to evaluate the ideas generated for them. So for each researchers, we generate 48 research ideas with 3 different ways. One is like use concept predict to be high impactful, and one method is randomly select concept pairs from the knowledge graph from the knowledge graph from the 2 researchers, or we don't give the concept but ask the GPT to come up with the concept. And with that, we ask them, we randomly shift it and then ask the researchers to evaluate whether this is interesting for them to work from with a score from 1 to 5. 5 is very interesting, highly interesting. 0 is not interesting. And it's roughly 25% they ranked like very interesting, although many are not interesting. But if you have a small portion of ideas that is very interesting or maybe very feasible and so on, that's already very good. We also then classify it into these 3 ways because we use 3 ways to generate the project. And you can see there's no big difference between them because there are many reasons behind it. So one thing is like we correct the knowledge graph, but we ignore the social information, like the author information and so on. So some ideas are interested, but actually only for their co-authors, not for him. So there are many things can be improved, but there are roughly 3,000 ideas are using the concept from the knowledge graph. So we can think in a different way as we already have the evaluation data set. So we can think about whether there are some research, like a scientific research interest from the researcher might have some correlation with the features from the concept pairs. So we do look at some concept pairs and then it sees that there are some correlations. For example, that if the 2 concepts has been connected very often, namely they have been investigated very often, so it seems the idea ranked by the researchers is not interesting, so the ranking score is low. Or if this concept has been cited by many papers, seems this is also not interesting for the researchers. So we can think a different way that maybe we can use the human evaluate data and then the knowledge graph, the concept from the knowledge graph to train a new network or train a model to suggest a more interesting research project. So we take the concept research ideas, like give to the researchers, and then take their ranking score, and then for each research project, we have the concept pairs, so we know the features. We give the features to a neural network and predict whether this is interesting or not, like whether the ranking score is big than 4 or small than 4, and so on. We make it as a binary classification. In addition, we can also use a slightly different way that we can ask a language model to rank it. So we randomly give a random pair from the 2,900 ideas and ask a language model that which is more likely to be ranked higher respect to the researcher. And then in general, we can find that we can somehow use a knowledge graph and then human evaluation data to predict somehow the researcher's scientific interest. So that such that we can maybe later in the future to fine tune the features or change the models to generate a more interesting research project for scientists. In addition, that we also are interested in that we are also interested in that if there are small portion of the ideas will be interesting, so we look at the procedure as well. So these are 2 different ways to generate ideas. One is design experiment, another is like design also ideas, but from a natural language text way. This is more giving the concrete experimental blueprint. This gives you some ideas that could be interesting to explore. But the things that sometimes the language model give the ideas might be too broad and maybe not very practical to implement. So one thing is like, can we put them together or somehow use build a language model or like a language agent system to have access to different tools and then come up ideas and then also give you the experimental blueprint. So that's what I will briefly discuss a bit about AI Mentor. We recently published, put on archive. So the idea, the workflow is quite simple. So we somehow try to mimic the group of a group of a team. So like a lab. So with computers. So one agent is like does idea generations. It contains mainly a sub agent try to come up ideas and then generate certain idea pools. And then we have also a team like doing pick the ideas and implement it. And then with access with the tools that I explained before, use PySUS or maybe use other design tools. You can also apply to this workflow and in the end give you the blueprint or the experiment. So far, we also do we don't automatically like generate the or write the paper from computer. We still have we also implement ourselves at the moment, try to understand the ideas and generate and write the paper from humans researchers. So the idea generation part is like you have research agent and novelty agent and judge agent. So then it's like the research agent have access to archive and also the existing implementations, namely from PySUS, we have 100 experiment has been give the solution. So we also provide such examples to the research agent, and also we give the impact forecasting or the SIMUS. As I said, this give you unconnected pairs that will be interested or be high impactful, and then they do this with try to come up ideas, and then there's a novelty to check whether this idea is novel respect to whether this has been done in previous literature or has been done in the examples we have provided. And if it passes, then the judge agent will judge whether this is valuable for the tool to implement. And if not, then they will have this feedback give back to the research agent, and then with this group try to come up ideas. And then we have this research pool. So namely that is a novel and also feasible experiment. And then we have this idea implementation agent. So it will try to convert this text idea into a config file that can be implemented or can be run by the computer tool that we developed before, use graph representation to discover new experiment. So we give the config file like human instructions to the tool, so it will automatically run the config file to give the solutions. So the idea implementation agent is more like translate the text idea into a concrete config file that can be accessed or run by the PySUS. And with that, this is just one run how it look like. So the research have some ideas, and then the novelty will check whether this is interesting or not. If accepted, then it will judge again whether it is interesting, and then it go to the expert to implement, try to translate this text idea into a config file, and then it will automatically run the design tool like the PySUS, and then give the final solutions. And the final solution is also written in a config file, and one can represent this right in this graph and then translate to an experiment setup. And with this, these are some solutions we found. For example, that's entanglement swapping for logic entanglement. Of course, from there we try to understand it, and then we inspired from that, then we write like this topic in a more general way, how we can entangle particles that never interacted before, and they are entangled. So without using entanglement swapping and so on. And also it find some like non-local swap gate between two different locations. We don't directly implement this idea, but inspired from the idea, we formulate in a different way that we can maybe train to automatically discover non-local opportunity gate from this idea, not just the swapping gate, but many other gate. So that's why we can have another paper about this when we try to generalize and understand the idea behind the solution found by the agent. And it also gives many other ideas we haven't looked into further, but these are some ideas that might be interesting to explore further. So we try to have the idea, we have the idea from the agent, and then we try to understand it and interpret the result and then formulate ourselves. So far it's like we have the steps that you can generate ideas and then experiment the blueprint, but it's not completely fully automatic, such that we still need to try to understand ourselves and then write a paper. So these are the three ways that we can use computers to help field in, for example, quantum optics. So one thing is like we can use computer to design experiment, or we can use computers to come up new research directions or research collaborations for scientists that will be impactful and interesting for them. Or even we can like we don't target any target, give some specific goals, but ask let the computer to come up ideas and then give the concrete experimental blueprint. Maybe in the future, maybe it can try to have some language model or agent to interpret the result and try to understand the result, and then maybe in the future directly write the paper or have access to the real experimental setup to do the fully automatic lab. And that's rough research topics that I would like to explain today. Yeah, thank you very much. Do you have any questions? I hope I didn't run over time.
Wow, bravo. I mean, I'm super shocked even. It's amazing. Wow, congratulations. Like you picked a super interesting research topic. Wow.
Thanks. I try to skip many details, so but you can ask questions. Sorry. I hope you can yeah, understand the idea at least.
There are for sure. I have a lot of questions, but that's like whoever has questions, please go or comments. Like really, congratulations. It's beautiful and very impressive, and maybe a bit like science fiction.
Okay,
like,
so I have one question first.
Yeah.
Well, first of all, thank you for the talk. It was really interesting. With regards to the knowledge graphs, in those, are you using directed graphs or undirected ones?
Good question. We are using undirected ones. So
Okay.
yeah, so we don't have directions. So we just have like a undirected graph, namely that if they appear in the abstract, then there's edge between them, but there's no direction and so on.
Okay.
Yeah.
And have you considered using directed graphs? Because, for instance, in learning sciences, I think knowledge graphs are being used right now. And an important point is that you have some sort of direction, that certain concepts appear before other ones can be learned, in a sense. Because if you don't have the background or the foundation, you cannot come with that idea. Have you considered that? Maybe it's not feasible because from the abstracts themselves it's not enough, but what are your thoughts on that?
Yeah, I think that's a very nice direction and question. And I did thought about directed graph, but I thought maybe one can construct with somehow like a hypergraph, so you can have more additional information instead of like an edge between the two concepts. But maybe there's a reason why these two concepts appear together. I don't know what the format would be nice to explore. I thought about hypergraph, but maybe a directed graph might be interesting to explore. So I think with a different format of the graph, one can maybe increase add more information from the paper. So make the knowledge graph more enriched and then more precise, I think. But I haven't do that yet. I thought it's a nice direction to investigate, maybe study.
Okay, thank you.
Someone has another question. Otherwise, I would like to ask you in slide 24. You were generating the GZ state.
Yeah.
How many modes do you have, and how does this scale with the number of modes?
Okay. With this particular case, we only go to 4-particle, and I think 6-particle. We didn't go further.
Okay.
So we train the model with 4-particle quantum state, like a graph with 4 nodes and 6 mode. Yeah.
So isn't there a possibility that finding a GH set producing, I don't know how to say this, like a GH set preparing circuit is highly likely, and then I mean, well, actually you're sort of showing like the distribution, right? Of
yeah, so it's like we give some random setup, and then it can try to design the kind of perfect setup, or the setup with high fidelity. So which means one can use the neural network as a physical simulator, and then apply optimization, try to change the input to get the solution that respect the one you are interested. So
okay,
it's not.
Yes. I'm trying to find some sort of connection between these variational quantum circuits where the probability distributions concentrate around like something, and then it becomes kind of difficult to scale it up. So
yeah, for the scalability, I think one need to. This is not very scalable. I think because it only trained for specific data set, so it's like a kind of surrogate model on 4-particle, 6-particle. So if you go a bit larger, then one have to retrain. Yeah, so it's not so scalable in this case. But the idea can be expanded, I think.
okay. And in this aspect, I wonder how much like quantum computing machinery can you import here? Like if you think very ideally like trying to apply quantum search algorithms to this setting and to boost a bit the setting, like applying Grover or something like that.
Oh, that's an interesting question, because in our case, we don't use quantum machine learning at all. We just have the physical simulator. We do classical optimization or classical machine learning. So with quantum machine learning, namely, like we can use maybe quantum hardware to design experiment. But I don't know whether it. But maybe it will have advantage, will be faster, but I cannot say how fast or somehow, because I didn't do that. But it will be interesting to explore. So I cannot guarantee that it will be faster or not. Yeah.
Sure. Maybe it's a theoretical work, but because I was thinking on, do you know when you study like transformations of genitals, then you get sort of a quantum channel, and then you can think on a super channel that transforms channels into channels. And then people studied the hierarchies. Like if you think on like super channels that transform super channels, and super channels that etc. And then this hierarchy collapses. Okay, and I was thinking, like, if you have studied if there is any hierarchy of like your algorithm that optimizes experiments, and then you think on one algorithm that optimizes your algorithm that optimizes experiments, and so on and so forth.
Oh, that's very cool somehow, but I don't know how to do that so far.
Okay.
Yeah.
Just a super random thought, but maybe it was pointing in your direction. And someone else has a question. Otherwise, I would like to ask something else. Like, how easy is it to? I never explored this at all. Like your Pytheus or the Suma, the thing that Carla did. I think.
This
But
one.
how easy it is to import all this machinery to use it in like even a research group that is not technical at all, like from human sciences. This might be super useful for people doing, I don't know, sociology or economics or I don't know, literature even.
Sorry, if I got your question correctly, do you mean this workflow will be whether this workflow is general enough for other field?
No. I mean, I'm pretty sure it is general enough, but how easy it is to borrow it. Like if my colleague from the literature department wants to apply this to study the theory of there is something called teoría literaria, literature theory, which also connects a lot of authors.
Yeah, okay. I think for experiment design part, mainly if one can address these 4 parts, then one can do things easily, I think. For this part, it's just different optimization techniques or neural network or different machine learning techniques. Not necessarily quantum machine learning, but one can also think about quantum version. And then the main thing is like how one can construct a large space that contains more experiment designs inside, or make the combinatorial space, or make the space large enough. If you make it very narrow, then it's more goes towards to the pure optimization task, like a simple optimization task instead of discovery. And then physics simulator, then it's very difficult to say because it respect to the field that you are interested. One can do a optic simulator or some specific simulator. Maybe in chemistry they have their own simulator to simulate the vibration of molecule or something else, and then you define some objective or that somehow like a loss function that you want to use.
I was more pointing towards the predicting the scientific research direction.
Oh, okay, sorry. For that, it's very. Because you talk about the Microsoft, I got confused. For this, it's easy to explore. One can easily do that because all the data set are basically open available, so one can extract this concept with rapid key rate extraction based, which is like a statistic text of the. It's a statistical method, so then you can have a lot of concept very fast. And then for the main time consuming part is you want need to fit the concept a bit. either you do it manually or you can ask GPT to filter it. It's a bit tricky, yeah. So one can like use label some concept and then fine tune some language model to learn it, and then maybe ask let the language model to extract the concept automatically in a different way. So, but the workflow is quite simple. So it's like you just have the papers that are already available. This dataset is also available. And then you look at a specific field if you are interested, or you look at many field. And then you construct this knowledge graph. It's just you can consider it's a dataset with age, and then contains information. So this is quite easy to easily use and adapt. Yeah. Just one thing is like for the dataset is large, so maybe sometimes one need a higher memory CPU. But afterwards, after you construct the knowledge graph, and then for the training part, it's not so expensive. One can use a normal CPU or GPU. You don't need to use very fancy ones, but one can also use fancy one. Yeah, but it's very easy to use. Yeah.
Here, impactful means like a lot of citations, or how do you measure impact here?
Yes, here the impact is we use citation count within the 3 years or 5 years, depends how many years you are interested, as an approximation as impact. There's no good metrics for impact. So
Exactly.
so that's why we use citation, which is like widely used by others, although they have a lot of problems. But yeah, we don't know what's the best metrics for impact. Yeah, so that's why we use these simple metrics.
And just out of curiosity, and this I will shut up because too many questions from my side, but have you used all this to understand the social dynamics, like in social media, for example? Like instead of citations, you can, I don't know, replace citations by, I don't know, social media likes or comments or Twitter posts. We had a talk, no, there was not a talk from this group, but there is, I don't know if you know Juani Bermejo. She has studied with a colleague. She's from Granada. She has now a quantum computing group in Granada. And she has studied actually trying to predict trends in Twitter. That was before Elon Musk bought Twitter, and then the data was available online, and now it is not anymore. But she was doing super cool things with this aspect.
Yeah, that's a very good question. To be honest, I thought about I'm not sure about Twitter and other social part, but because Archive and this by Archive, they also have information, and the research institute different information from the dataset. So potentially maybe one can add the also information inside the knowledge graph. Maybe see this how the collaborations with the researchers in this topic and so on. Could be interesting to explore, but yeah, just for simplicity, we didn't think further. We just think about
yeah. What you're saying is that actually in SciRate, this happens in our community, like the quantum tech or machine learning community. In this clustering happens as well with the comments and whatever, like the most sci-rated papers, which some are like amazing, like yours or whatever, but some are just because they have a lot of repercussion in social media, and there is also more information to put, yes, for sure.
Yeah, that's for sure. Yeah, would be nice to look into that. How also I don't know how one can have for example, if one look into the Twitter, like or not like this type of data, I don't know how one can get such data set. to be honest.
How to scrap the data on
Yeah,
social
yeah.
media?
Yeah,
There are many, I think there are many tools, but there was a Twitter analytics like a few years ago, but now I don't know. But I mean, one should design an algorithm to scrap, like a perplexity that scraps with LLMs.
Oh, okay, I see. Interesting.
Yes. Well, I mean, maybe that someone else has a comment or something.
I have another question related to the graph representation of the experiments. Have you identified any kind of structure of the successful experiments that your workflow is finding, or any sort of identifiable features that are maybe of interest in the graphs that you are finding?
No. I think we find some nice structures from the graph representation, to be honest. So for some quantum state, we have some, we generalize it, and one can easily generalize with the graph representation. For example, geometry state, like a 2-particle, 4-particle, 6-particle, 2D geometry state. So in the graph representation, it's just a ring. So when you increase the number of particles, you increase you expand the ring graph. So it's very nice structures. And for W state, we can have a book graph. So it's like each page is somehow like the term of the quantum state. So when you add more, then you add one page. Yeah, so we find these are very interesting and nice structures. But for others, there's no clear structure when you generalize to other state or go to high dimension or go to multi-particle. We don't see whether there's a nice structure. Yeah. But
Okay.
some of them have nice structures. Yeah.
And have you considered using any sort of generative model over these cases where there is no clear structure? Or maybe it's not, the application would be not so direct?
I didn't think about that.
Okay, thank you very much.
Sorry, I didn't understand your answer, Shemay. You didn't think about that, or?
I didn't think about use like a language model to see the structures or something from the graph representation. I don't know how also. Yeah.
Okay, because I mean, maybe it's not related to what Uriol was saying, but I think it might be. We were thinking in the past on there was a paper very basic that was classifying the quantum state according to the entanglement class it was belonging to. Like if you have many, like you said, no, when there is many parties, you can have different type of entanglement, like G state, but also like W state, and also entanglement between pairs. And then there was the question to import all this machinery from simulating like super big quantum states with this, I don't know, Uriel, how to say it, IQP, is it? Instantaneous quantum polynomial circuits or something like that, where you can study very complex quantum systems and trying to understand if you can run generative models to generate the states belonging to that class, to each class.
Oh, I see. Yeah. Okay. From this graph representation, it's not clear for me that whether the structure, particularly whether some state can be generated, because for some quantum state you cannot generate with restrict a certain number of node. So one need to add some additional node, namely ancillary photons, to construct some quantum state. So yeah, so it's not clear for me how to do that at the moment.
But you have a continuous
yes. I have continuous variable, but for some quantum state you want to generate, for example, let's say I want to produce high dimensional 6 particle GHZ only with 6 photon. This is not possible, but you can add additional node, namely additional photons, then you can do that. Yeah, so, but with how many additional photons is quite unclear. You can add more or add, yeah, it's a bit tricky. One need to play around with the software. Then we can find, and then with that maybe we can further do the thing you're saying.